Hi everyone, welcome to Deep Learning Talks. So today we are going to talk about why do we have feed-forward neural networks or these linear layers at the end of multi-headed attention block. So we have seen in case of a transformer, we have something known as token embeddings. They get added with positional embeddings. Then this linear added input goes into the multi-headed attention block where multiple heads of attention are computed. Now at the end we have a feed-forward neural network that captures the output of a multi-headed attention block. Why do we need it, right? So feed-forward neural networks turn all of these existing representations into decisions. Attention is only producing contextual representation. Attention is not making decision. Attention is not adding a lot of non-linearity, and producing this representation is not equal to decision. We need the ability, or our transformers need the ability to make the decision. What kind of decisions do they need to make? In this case, let's imagine that if we have a decoder only transformer, we are going to make in that case we are also kind of making a decision. The decision can be a class or it can be a regressive decision. In case of RNNs, we have seen that CNNs produce spatial representations, right? Similarly, RNNs also produce sequential representation, whereas transformers produce contextual representations through attention. So all of these three neural networks, or let's say extensions of neural networks, are dealing with different modalities and they are producing some different representations in their own world. Now, these representation is not equal to decisions, right? So we need a decision making system, a decision making neural network. We need someone, some block, some sublayer, some linear layer to answer what should we do with this information. Now that we have produced this meaningful information for the text modality using attention, for the image modality using CNNs, now what do we do with this? So this information for CNN helped us capture a lot of deeper hierarchical representations of feature maps or images, which are great at detecting patterns. And same for attention. Attention helped us understand the contextual representation between token 1 and token 2 and so on for all the tokens, which is very good at understanding the language. And similarly for RNNs, RNNs helped us produce the hidden state, which is helping us understand the deeper sequential relationship between the language or between any sequential data that RNNs are dealing with. So now what does a feed forward neural network is actually doing? So the first thing it's doing is, I mean, largely it is helping us take the decision, right? The first thing it's doing is it's helping us add a lot of non-linearity. Most of our information is nothing but dot product and weighted sums and linear projections, which we call as information, which we also call as representation. Now the feed forward neural network is helping us add and fuse in a lot of non-linearity, introducing activations on all the neurons by introducing non-linear activation on all the neurons. In case of transformers, we have seen that multiple heads of attention are produced and then they are concatenated and they are multiplied with the projection matrix. Now the projection matrix is a linear operation. It's like a dot product with the multi-head attention concatenated output. The feed forward neural network mixes them non-linearly, right? So there's a big difference. So feed forward neural network, wherever we have to add in non-linearity, helps us in producing non-linear functions, in producing non-linear representation all of this information all of this information. Since we talked about decisions, all the decision boundaries lives in these feed forward neural networks. So when a model predicts a class, when a model predicts a probability, when a model predicts the next token, the main output head is nothing but the feed forward neural network. All the decisions made by the output head is nothing but the feed forward neural network, whether you see it for CNNs or RNNs or for transformers. Because at the end, the final step is always the function approximation problem. The neural networks are also known as function approximators, right? So in case of CNNs, we always see that there are series of convolution blocks and then we have nothing but a multi-layer perceptron classifier that helps us identify the difference between a cat and a dog. In case of transformers, we see an LM head, which is the language model head, which helps us predict the next token in the sequence. In case of RNN, we also have dense output layer after the hidden states, which acts as the memory. So hidden states acts as the memory, and then we have a dense output head, which helps us do the prediction of the next token in the sequence. Along with this feed-forward neural network, or multi-layer perceptron, or the language model head, or all of these, deep neural network layers, or the linear layers, whatever we call them. So they have multiple names. So they also help us with trainability, right? So we have infused a lot of non-linear activation functions, a lot of non-linear transformations. We have a lot of trainable parameters. We have an output head. At the end, we just want richer gradients. We want richer representation, better parameters such that our loss function is optimized. So these feed-forward neural networks also helps us in trainability. So if you want to build a mental model, the representation, the information that is captured in CNNs using convolution block, that is captured in hidden state using RNNs, that is captured in transformers using attention, is basically helping us organize or structure the information better that is there in the data modality that we're dealing with. Now, the feed-forward neural network, as soon as it comes into picture, it is helping us in reason. It is helping us in making the decision. It is helping us in doing the computation. It is making the training easier. It is helping us add nonlinearity. My closing notes would also help you focus on one more paper. So just like we have attention is all you need, we also have a paper that was published, I think, by John Hopkins University, by someone at John Hopkins. I don't exactly remember the name, but the paper name was Attention is Not All You Need. So that paper focused a lot on the impact of feed forward neural networks. So yeah, I think that was it from my side. It's very important to understand different blocks in any architecture. What is the role of each block? And if we remove that block, what is going to happen? And if we add more of those blocks, what is going to happen? So I hope this information made sense to you. Thank you.